Hi Aviva. So for my first demonstration, I'm going to use a PVC pipe, which I drew right here, and a fur cloth. And when I rub those together, electrons transfer from the fur cloth to the PVC pipe, leaving the fur cloth a net positive charge and the pipe a net negative charge. And then when I bring it over to a stream of water drawn here, the water molecules are polar, which means that there's a negative end and a positive end of their charges. So when a negative charged object comes near the stream, the water molecules will align themselves so that the negative is repelled, like facing as far away as possible from the negative charge over here, and the positive side will be facing that negative charge. And since this side of the stream of water is now positively charged from the realignment, the water will be attracted to the rod as it goes by. And that'll make the stream of water move towards the pipe. When charging by induction, we start with a neutral object that has no net charge anywhere on it. You can see that there's an equal number of protons and electrons in it, and they're evenly distributed. When you bring a charged object over, in this example we have a negative rod, all of the electrons in this object are free moving, so they can all move away from the electrons in this object because they're repulsed by them. The protons can't move, but the electrons can move freely within this object. So once they all migrate to the end to get away from the negatively charged object, what you get is one side is more negatively charged and one side is more positively charged. Since the positive side of the object ends up being closer to this negative rod, it is now attracted to it and it can start moving towards it due to an electrostatic force. And I'm going to demonstrate this with the same negatively charged rod as before and with a cat food can because I don't drink soda. I forgot to mention before that aluminum is a conductor, which is what enables electrons to move freely in this can. So right now it's at rest. Cool. And I was able to do that without even touching it. Now that we know how induction works, I can show you my electroscope. So this top ball here is made out of aluminum. It's connected to more aluminum going under the cap, and then there's two little aluminum leaves dangling off of it. So they're light, they can move easily if any electric charge happens. So I'm gonna charge this rod, give it a negative charge, and then see what happens when I bring it close to the ball. So if you watch the bottom of the leaves, they're gonna pull apart when the rod gets close, and then they're back to normal when the rod goes away. So this happens because when I bring a negative charged rod over here, this material is aluminum foil, so it's a conductor, all the electrons move freely. Having a negative charge around it will repulse all of the electrons that are inside of this. So originally this is neutral with an electric charge over here. All of the electrons are trying to move as far away as possible from the rod. And they have nowhere to go except for the bottom of this apparatus because they don't have any grounding or anything. So what happens is all the electrons go to the bottom of the leaves. And when that happens, we have two leaves sticking out like this, negative charges at the ends of both of them, and they repulse. So they split apart. That's the repulsive force between them. And then without the rod there, the electrons can move back to their neutral state where they want to be, and then it's back to normal. See how their resting stance is kind of like this. When the rod's over there, they go like, whoop. Yeah. So this time we're gonna try this a different way. Okay, so my rod is negative. I bring it close. The bottom of the leaves pull apart because of the negative charge, but when I touch it with my finger, they don't pull apart anymore. I let go of my finger, nothing changes. When I pull away the rod, they go apart. So when I touched this, my finger became a ground wire for the electrons, like an escape route. So once my finger does its job and it pulls away, the whole thing has been neutralized until I pull the rod away. And this time, without the negative rod there looming over it, there's a net positive charge left in it, which is why at the end, with nothing touching it, the bottom of the leaves flared out because there is a net positive charge all over the metal now. Okay, now I'm going to demonstrate a method to test the polarity on the charge on the electroscope. So I'm gonna do what I did before. I'm gonna get a negative charged rod, then hold it close. The leaves go apart. When I ground it, they go back to neutral. Pull my finger away, they're still neutral. Pull the rod away, they go apart because of the positive charge there. The positive charge is still at the bottom, so I have to hurry and charge this glass rod. The glass rod will have a positive charge, and if they go apart more, then it's positive. Okay, I tried every possible cloth on the glass rod and could not get a reaction from this with it, but the negative charged rod worked, so I'm just gonna work with what I already have. So we started by bringing the negative charged rod close, which made these go apart. So from that, we know that all the electrons were repelled by the negative rod, and they moved to the bottom, and having the same sign at the bottom caused a repulsive force. Repulsive, making the leaves stick out like that. And then while I was still holding that rod there and the leaves were sticking out, I touched this with my finger. This time the electrons had somewhere to go, so they all went through my finger. The leaves came back to a neutral state, which is here, and I grounded this with my finger. Electrons escaped. So in the aluminum foil, there were less electrons than protons. When I moved the rod away and the rod is no longer repulsing the electrons in this, that means the electrons move back to a uniform distribution, or the best that they can do, because now there's less electrons than protons, and no matter where the electrons go, there are two same side charges at the bottom, both positive, that are making them stick out like this. And then if the glass rod had been positively charged and we held it near the ball, then the bottom of this would pull apart even more, because then the electrons that are still left in this would all move to the top, and the bottom of this would become even more positively charged. So from that method, we can conclude that if this metal component, the ball and its stem and everything, is already positively charged, and we hold a positively charged object near it, it's going to spread apart even more. And that's how we know that this is positive and this is positive. Then the same thing would go for a negative charge. If this was all charged negative, we bring the same sign charged object over, it would make the repulsive force even bigger at the bottom. And then grounding the electroscope is good for neutralizing it. It'll make the tendrils go back to a neutral position, because the electrons can come in from my hand or they can come out. Another note I want to add is when I am touching this ball with my finger, the ball is not just taking electrons from my finger.
The ball is connected to my finger, which is connected to my arm, which is connected to my whole body, and my feet are on the ground. So it is a grounding wire for this apparatus and a way to discharge it. Right here, I have an electrophorus, which is used to generate and store electricity. So this part is a conducting material. I have aluminum foil with a little insulator handle for me to move it without touching the foil. And then this is the insulator that I am going to be putting this on. So to do this experiment, I start by charging the insulator. Now I'm placing my conductor onto my charged insulator, and I'm going to touch a corner, and I just got shocked. I don't know if you heard that, but it made a shocking noise. I felt it, and the corner of this foil lifted up to come touch me. So what just happened is that the insulator was charged, the conductor touched it, and the charge distributed evenly between the two materials. But since one was already charged, there was still an excess of electrons, assuming that the insulator was negatively charged. And when I touched it with my finger, the free moving electrons, since the conductor has free moving electrons, came through my finger to be grounded. And that excess charge flowing through my body, when there's enough of it, will create a spark like I was able to hear and see and feel. Okay, now I'm going to show you that those results are reproducible. So I'm going to charge this again. This goes back on. And now, if you listen closely, I just got shocked. I'm going to lift it up. It's not touching it anymore. And I got shocked again. If I put it back down, I got shocked one more time. Now I'm going to show you in more detail what's happening when I'm doing those demonstrations. So with the electrophorus, I start out with the insulator, and on its own, in its natural state, it's neutrally charged until I rub it with the fur. The fur starts neutrally charged too. But when I rub the insulator with the fur, electrons transfer over from the fur into the insulator through friction. Making the fur positively charged and the insulator negatively charged. So there's a bunch of electrons lining the top of the insulator. And then I bring in the conductor, which was the metal plate. The conductor starts with a neutral charge, but when it touches the negatively charged insulator, all of the electrons in the conductor move to the top of the material to get as far away as possible from the negative charge down here. So then in comes my finger. My finger is the grounding here. And when my finger touches it, these electrons that are trying so hard to get away finally have a way to get out. And that's through the grounding wire. So after my finger grounds the conductor, then we have a positive conductor, because the negative charge here scares out a bunch of the electrons, and we're left with more protons than electrons, which gets you this, a net positive charge. But it doesn't end there, because what makes these results reproducible without having to charge it again is that when I touch the plate again with my finger while it is now positively charged, electrons flow in from my finger into the conductor to balance it out and give it a neutral charge. So now it's back to neutral, and then, as you saw before, I put it back on the insulator, and the insulator is still negative, which means all of the electrons that just got back from me grounding it move up to the top again, making this whole thing negatively charged on the top. It's back to where it was over here. So if I put my finger on it again, it shocks me again because electrons are leaving. They don't want to be there with the negative charge here. And we can repeat these two steps over and over indefinitely. Finally, I have these little papers here. Some of them are styrofoam, some of them are paper. And I'm going to charge this again. Put the negative charge there. Put my conductor on it. I'm going to ground it. And I'm going to lift it back up again. Now, since I've grounded it, like I showed you before, this is now positively charged. I put it over the papers. And some of them like rotate a little bit, but they should be attracted to this because initially these are neutral, nothing is making them charged. And when I bring over a charged object, there is charge separation in these little papers and styrofoams. And the charges that are the same as this are going to go as far away as possible, like to the, I guess, towards the bottom. And the charge that is opposite to this will be attracted and come out to the top. And with the attracted, more attracted side of these objects being closer to this, there's going to be an attractive force that should pick them up at an extreme, or at least like move them towards the conductor. Finally, I have these little papers here. Some of them are styrofoam, some of them are paper. And I'm going to charge this again. Put the negative charge there. Put my conductor on it. I'm going to ground it. And I'm going to lift it back up again. Now, since I've grounded it, like I showed you before, this is now positively charged. I put it over the papers. And some of them like rotate a little bit, but they should be attracted to this because initially these are neutral, nothing is making them charged. And when I bring over a charged object, there is charge separation in these little papers and styrofoams. And the charges that are the same as this are going to go as far away as possible, like to the, I guess, towards the bottom. And the charge that is opposite to this will be attracted and come out to the top. And with the attracted, more attracted side of these objects being closer to this, there's going to be an attractive force that should pick them up at an extreme, or at least like move them towards the conductor. Okay, that shocked me again. It's grounded. If I put this back over here, it should be reproducible. And some of them are moving a little bit. There's just a tiny bit of movement. But what is happening is that these pieces are attracted to this. So I can put it back on here, I can ground it up here, ground it down here, can hover it over these again, and it should reproduce each time as demonstrated on the whiteboard earlier indefinitely. Thanks for watching.